In the previous two videos, we looked at Riemann sums. We learned about left Riemann sums, right Riemann sums, middle Riemann sums, the trapezoidal Riemann sum. We also learned that a Riemann sum is used to estimate the area under a curve, and that the area under a curve can be written as a definite integral. So in this example, we're going to use a Riemann sum to estimate a definite integral. In this case, we want to estimate the integral from 0 to 18 of f of x dx. 0 is the lower bound for the integral, 18 is the upper bound for the integral. These are the same as the lower and upper bounds of our interval I. And we want to do this using an RRAM, that is a right Riemann sum with 4 subintervals. In this example, we're given a table. Using tables to calculate Riemann sums is the best way to do this. If you're given a graph and asked to find a Riemann sum, I would just take a minute and throw everything into a table. Once you have all of your numbers organized into a table, the Riemann sums are much easier to calculate. So first, let's plot these points just to get a visual of what we're doing. Here I've plotted 0, 6, 2, 13, 6, 15, 11, 22, and 18, 30 as 5 white points. If we want to calculate the area beneath f of x using the table, then we're forced to use each of these coordinates when finding the area of each rectangle. So that first rectangle would go between the lower bound of the integral, which was 0, up until our first coordinate, which is 2. Since we're doing an RRAM, we're using the right endpoint to define the height of that first rectangle. So therefore, the height of the first rectangle is equal to 13. If we then wanted to calculate the area of that first rectangle, all we have to do is multiply 2 times 13, and that would give us 26. The second rectangle would then span from 2 to 6, and the height of that rectangle is defined by f of 6, which is 15. The area of that second rectangle would then be 4 times 15, which is 60. Notice in this case that delta x is not the same for both rectangles. The delta x for the first rectangle is equal to 2, while the delta x for the second rectangle is equal to 4. Since the delta x differs for these, we will not be able to use that general form for RRAM that we showed before. We just have to calculate the area of each rectangle independently and then add them all together at the end. The third rectangle would then span from 6 to 11, and the height of that rectangle would depend on the right endpoint 11. f of 11 is equal to 22. The area of our third rectangle, A3, would be 5 times 22, which is 110. That fourth rectangle would then span from 11 to 18, and the height of that rectangle would be f of 18, which is 30. A4 would then be equal to 7 times 30, which is 210. We could then find the total area A by adding up the area of each of these rectangles. 26 plus 60 plus 110 plus 210 is equal to 406. So now I want to show you another way to calculate A when you have a table so that you do not have to look at the graph. When doing this for a right Riemann sum, we're going to use the right-hand f of x number from each pair. So just imagine that you drew a rectangle that spanned between x equals 0 and x equals 2. The delta x for that rectangle would be the difference between the x values. 2 minus 0 is 2. And then we just have to use the right-hand f of x value as the height. So the f of x we use in this case is 13. Then if you imagine drawing a rectangle that spans between 2 and 6, delta x would be the difference between those two x values. 6 minus 2 is 4. And then the height of that rectangle would be f of x is equal to 15. We do the same thing for the next pair. Delta x is equal to 11 minus 6, which is 5. And the height of that rectangle would be f of 22. Finally, the last rectangle would have a delta x of 7, and the height of that rectangle would be 30. So then to calculate A, all we need to do is put all this information together. For each of those imaginary rectangles that we've created around the table, multiply the delta x with the f of x value. So that first rectangle we would multiply 2 times 13. That would have been the area of the first rectangle. The area of the second rectangle would be the delta x equals 4 times f of x equals 15. And then also multiply the 5 and the 22, and then the 7 and the 30. Each of these terms gets added together. That would give us 26 plus 60 plus 110 plus 210, which is equal to 406. This second method gets you to the exact same answer without having to draw a graph. So typically this will be the fastest method if a graph isn't provided for you inside of the problem. Let's look at the same problem, but in this case we're going to use the LRAM to estimate the integral. That is, we're going to use left Riemann sums. And when doing a left Riemann sum, use the left-hand f of x number from each pair. Like we did in the table for the right Riemann sum, just imagine drawing a rectangle that spans between x equals 0 and x equals 2. The delta x for that rectangle would just be the difference between the x values. 2 minus 0 is 2. And then for the height of this rectangle, we use f of x is equal to 6. The next rectangle would span between 2 to 6, so the delta x would be 6 minus 2, which is 4. And then we use the left f of x from that pair. F of x is equal to 13. The rectangle spanning between 6 and 11, delta x would be 5, and we use f of x equals 15. And then for the last rectangle, delta x would be equal to 7, and we use f of x equals 22. All we need to do now to calculate a is to put all this information together. Just multiply the numbers on top and bottom of the table for each rectangle. So the area of the first rectangle would be 2 times 6. The area of the second rectangle would be 4 times 13. The third would be 5 times 15. And then the fourth one would be 7 times 22. This would give us an answer of 293. And then the final example we're going to look at is estimating the integral from 0 to 18 of f of x dx using a trapezoidal Riemann sum with 4 subintervals. So basically we're just adding up the area of 4 trapezoids created by this table. The height of the left side of each trapezoid will be the left-hand number from each pair, and then the height for the right-hand side of each trapezoid would be the right-hand f of x value from each pair. Then all we need to do is just sum up all of the trapezoid areas. Notice in this case that the delta x changes for each one. That means that we cannot use the simplified trapezoid formula that we calculated in an earlier video. To calculate the area of the first trapezoid, we use the first two f of x values as our b1 and b2. So we add these two together, 6 plus 13, multiply that quantity times delta x, which is 2, and then divide it by 2. The next trapezoid, b1 and b2 values would be 13 and 15. We add 13 and 15 and multiply that quantity times the delta x for that trapezoid, which is 4, and divide it by 2. The third trapezoid uses 15 and 22 as b1 and b2. That would be 15 plus 22 times delta x equals 5 divided by 2. Finally, we use 22 and 30 for the last trapezoid. So we add 22 and 30, multiply that quantity times 7, and divide by 2. If you throw all that in the calculator, you'll find the estimated area is 349.5. When we calculated an RRAM, we found the highest estimate of these three was 406. The LRAM gave us the lowest estimate, 293, and then the trapezoidal Riemann sum gave us 349.5, which was somewhere in the middle. And we would expect this 349.5 to be the best estimate out of the three.